Hello, I'm N J Wildberger, and today we're going to talk about lines and planes in 3 dimensions and how we represent them with equations. Before we move to 3 dimensions, it's important to understand the 2-dimensional situation very well. So let's start by talking about lines in 2 dimensions. Here is the usual affine grid plane with x-axis and y-axis, not necessarily perpendicular. And let's start with an example of a line. Say this green line here, line L. In ordinary high school mathematics, we learn that lines are represented by the equation y equals mx plus b. That emphasizes the fact that y is a function of x. In that notation, this line here would be the line 1/2 x minus 1, because the y-intercept is minus 1, and the slope of the line, the delta y over delta x, is 1 over 2. There's the slope, and there's the y-intercept. Now that's very appropriate for a calculus orientation towards lines, but in linear algebra we want to think about them not as functions, but as primary geometrical objects. So for that, it's much preferable to think in terms of x and y as having equal value or equal weighting. So we're going to treat x and y symmetrically, and we're going to prefer to write an equation of a line in the form ax plus by equals c. So we can rewrite this equation here if we multiply by 2 and bringing the x and the y's all on one side and the constant on the other side. Then we get x minus 2y equals 2. That's also the equation for that line. All right, let's observe that there are 2 important points on most lines. The places where the line intersects the coordinate axes. To find the y-intercept, we can set x equal to 0. If we start with the general equation ax plus by equals c, and we set x equal to 0, then we can solve for y. Y is equal to c over b. And we get the y-intercept with coordinates 0, c over b. In this case, this one here. And if we set y equal to 0, that means we're getting the point on the x-axis. We get x equals c over a, and so the point is c over a, comma 0. That's, in this case, the point 2, 0. And it's important to remember that whenever we divide by something in mathematics, we have to make sure that that something is not equal to 0. So these formulas only work when the denominators are not 0. This is usually called the Cartesian equation of the line, and it's going to play an important role for us in linear algebra, of course. But there are also other ways of representing a line. There is also a parametric equation for a line, and that involves a parameter that might be, say, lambda. For example, if we have 2 points A and B on a line, then the line can be described by the affine or barycentric combination 1 minus lambda A plus lambda B. That represents an arbitrary point on the line, and depending on what lambda is, that gives you different points on that line. That's called a parametric equation of the line, and let's have a look at what it looks like for the line we were talking about in the previous example. We might take the point A to be 2, 0, B to be the point 6, 2. In that case, this expression is 1 minus lambda times A plus lambda times B. And we could put things together. The x-coordinate is 1 minus lambda times 2 plus 6 lambda from there. And the y-coordinate is 0 here and 2 lambda there. If we expand out and bring the lambdas together and the constants together, we get altogether 4 lambda plus 2, comma 2 lambda. And we can leave it in that form, or we could also write it like this, which is instructive, to take the parts involving lambda out, and the point 2, 0 here, plus lambda times 4, 2. And now what I'm doing is I'm writing this 4, 2 as a vector, because it represents the vector joining this point to this point. So the geometrical meaning of this is we're starting at the point 2, 0, and then we're going some multiple of this vector here. And since it's a vector, I write it as a column vector. So there's a point on the line, that one there, and there's a direction vector for the line. And neither of these is unique. We could have chosen, instead of 2, 0, we could have chosen that point, or any of the other points on the line. And instead of this direction vector, we could have chosen any multiple of it, positive or negative. So that's a parametric equation for a line. And so there are these two different ways of thinking about what a line is, or how to represent a line. There's the Cartesian equation, and there's the parametric equation. Here is an example of a standard kind of problem that we need to be able to solve, to find the intersection, or the meet, of two lines. So let's take the line x minus 2y equals 2, which is the line we've already been considering, and another line, 5x plus 4y equals 20, which is this line right here. We want to find where these two lines meet. In other words, we want to find the point xy, which satisfies both this equation and this equation. Well, in terms of what we've already done, let's rewrite this using our matrix language. This equation here, as a pair of equations, can be written as one single matrix equation, where the matrix is 1, minus 2, 5, 4, the matrix of coefficients appearing here. So the left-hand side becomes this matrix times the vector xy, and that should equal the vector 2, 20 on the other side. And how do we solve this equation, this matrix equation? We solve it by finding the inverse of this matrix. So essentially we're going to multiply both sides by the inverse of that matrix, isolating xy. How do we find the inverse of that matrix? Well, we first of all calculate the determinant, which is 1 times 4 minus 2 times 5. So that's 14. So we take 1 over 14. And then the matrix that's obtained here is obtained by taking, well, either remembering the formula or taking the minors of this matrix here and arranging them in a certain way. So I remind you that the minors are the things that you get by eliminating a row and column. Say through that one there, you just get this minor 4. And its determinant is 4. So we put that 4 there. The determinant of the minor corresponding to this position is just the 1, so it goes there. The determinant of the minor corresponding to this is that minor there, that's minus 2. But the minus 2 doesn't go here, it goes there. And the minor that's corresponding to this is the 5, and that goes not there, but in that position there. And then we multiply by plus, minus, minus, plus to get 4, 2, minus 5, 1. So I've stated that in the same way that we were talking about the three-dimensional case. Just reminding you that this is the same prescription as how we found the inverse of a 3 by 3 matrix. Of course, it's simpler in the 2 by 2 case, just to remember that we swap these two diagonal entries and we multiply the off-diagonal entries by minus 1. So when we multiply by the inverse of this matrix on both sides, we get this times this vector here. And what is that? Well, that's 8 plus 40, that's 48, divided by 14, that's 24 over 7. And the next entry, minus 10 plus 20, that's 10, divided by 14, that's 5 over 7. And so that is the coordinates x and y, which are the coordinates of this point here. The point itself was actually the square brackets, 24, 7, comma, 5 sevenths. This is just what we obtained by solving the matrix equation. So we found that point right there. We also want to be able to solve that problem if the two lines are given to us in parametric form. So the same two lines can be described in parametric form this way. The line L, this one here, is 2, 0 plus lambda 4, 2. There's the point 2, 0, and the vector 4, 2 is the vector that gives its direction. This line here, M, has a point 0, 5 on it, and its direction vector is the vector, say, joining this point to this one here. That's the vector that's 4 in the x direction and minus 5 in the y direction. So there it is right there. So these are two parametric forms, one in terms of a parameter lambda, the other one in terms of another parameter mu. So what we want to do in this context is to find where these two lines meet, to find the parameter lambda and the parameter mu, so that these two positions actually agree. So if we write this out as a point, it's 2 plus 4 lambda, 2 lambda. And if we write this out as a point, it's 4 mu and 5 minus 5 mu. So we want to find lambda and mu so that this point equals this point. Well, that's really two equations, because we want the first coordinate here to equal the first coordinate here, and we want the second coordinate here to equal the second coordinate there. So that gives us two equations in lambda and mu. And these two equations can be solved in exactly the same way as we did previously. We first write it in a matrix form, coefficients 4, minus 4, 2, 5, giving us that matrix there. The variables are lambda and mu in that order. And the right-hand side is minus 2, 5. We multiply by the inverse of this matrix. The inverse is obtained by taking the determinant, which is 20 minus minus 8. That's 1 over 28, determinant in the denominator. The rest of it is obtained by interchanging those two entries, 5 and 4, and multiplying the off-diagonal entries by minus 1. So we get the inverse matrix is 5, 4, minus 2, 4, divided by 28. And when we multiply both sides of this equation by that inverse matrix, we get lambda mu by itself on the left-hand side, and we get this inverse times minus 2, 5. And then we do the calculation. Minus 10 plus 20, that's 10 divided by 28, same as 5 over 14. And 4 plus 20, that's 24 divided by 28, is the same as 6 over 7. So we get lambda equals 5 over 14, that's what we were solving for, and mu equals 6 over 7. And to find the actual point of intersection, we use either of these two values, plug back into here, either 5/14 into there as lambda, or 6/7 into there as mu, and in either case we get the same point, 24 over 7, 5, 7, that we did in the previous example. So we see in particular that a matrix equation like this can have different interpretations. Right? In both of these two different techniques for solving the intersection of two lines, one in the Cartesian framework and one in a parametric framework, we both got equations with 2 by 2 matrices, and we had to invert them. But the interpretation of what the meanings of the variables were quite different. Here the variables correspond to the parameters that are involved in the lines, and in the previous case the variables were x and y, the actual coordinates of the point that we were asked to find. Before we leave the two-dimensional case, let's remark that there are some special lines that we should pay a little bit of attention to, because they're a little bit different from the generic line. First of all, of course, the x and the y-axis themselves are special. The x-axis has the equation y equals 0. And that simple equation is still of the form ax plus by equals c. It's just that the coefficient of x is 0, coefficient of y is 1, and the constant is 0. The y-axis, on the other hand, has equation x equals 0. Now, other lines which are closely related to these coordinate axes are the lines which are parallel to them. And they also have very simple forms. Lines parallel to the axes are either the form y equals some constant, say k, or x equals some constant, say m. So for example, this line here, parallel to the y-axis, is the line with the equation x equals 2. It means that every point on here has the property that its x-coordinate is 2. And the y-coordinate can be anything. There's no constraint on the y-coordinate. This line here, parallel to it, is the line x equals 3.5, or 7/2. This line parallel to the x-axis is the line y equals 1. I'll just point this out because sometimes these lines, even though they're simpler than the usual lines, cause students a little bit of problem because they're a little bit different looking. There's a few zeros in there. When we're talking about lines, it's often convenient to have some special notation to denote certain families of lines that are related in a particular way. So there are two such concepts, pencils and stacks. A pencil of lines refers to all the lines which go through a particular fixed point. So there's a point P. And if we look at all the lines going through that point P, that's like a bouquet of lines. We call that a pencil of lines. Not sure where the terminology comes from, but it's very established terminology. So all these lines in this pencil are concurrent. And that's just one pencil corresponding to the point P. If we chose some other point Q, then we would have a pencil of lines around the point Q and so on. Now, sort of opposite to that is what I call a stack of lines. Well, this is perhaps my own notation, but I think it's quite good terminology. A stack of lines refers to a bunch of lines which are all parallel. So all these green lines here, they're all parallel, and when together, that whole family of parallel lines we could call a stack of lines, because they're all stacked up one beside the other. There are different stacks of lines. If we choose a different direction, say that one there, then the stack of lines that it determines would be all the lines parallel to it. So a pencil is determined by a point, P, and a stack is determined by essentially a direction or a vector V up to a multiple. So this stack here, this one I've shown you, is determined essentially by that direction vector V or any multiple of it. Once you know the vector, then you know the stack. And now in terms of this terminology, we can ask and answer a very interesting and somewhat unfamiliar question, but one that I think many students will really appreciate seeing. The question is, what do all the lines in the plane look like? So this is a kind of a guiding principle when you're studying mathematics. If you've identified an interesting family of objects, for us, say, lines in the plane, then of course we study individual lines that we've been doing with Cartesian equations or parametric equations. But it's also useful and interesting to ask, well, what about all the lines? Is there something we can say about the entire space of all lines together? So that's the question we're going to ask. What does the space of all lines look like? So we might be asking, for example, how would we parameterize or label all of the lines? Well, one way of thinking about that is to say, well, let's choose a point P and think about the pencil of lines through P. So there's a point P, and we're thinking about all the lines through P. That's a pencil of lines. Now, for every line in this pencil, say that particular one there, call it L, there's a stack of lines. The stack containing L. That is all the lines parallel to that L. We see that we get every line this way, because every line, no matter where it is parallel to a line through P. And it's parallel to exactly one line through P. So by varying the lines in the pencil P, and then for each one of those lines considering its corresponding stack, we are running through all the lines in the plane. So topologically or geometrically, what does the pencil of lines through P look like? Well, the lines through P naturally form a circle of lines. Why is that? Well, it's interesting to think about this circle here that I've drawn through P. If I draw that circle through P, then every line in the pencil at P intersects that circle, certainly at the point P, but also in one other point. Okay. And every point on the circle determines such a line. That's true with the exception of the tangent line itself. That only intersects the circle at that point. In fact, it sort of does a double intersection because it's tangent to the circle there. And that means that we can associate to every point on this circle a line in the pencil, and every line in the pencil is associated to exactly one point. So we say that topologically, the pencil of lines through P is a circle. And what about the stack, say parallel to a line L? If we take that line L and ask, well, what does the stack of lines parallel to it look like? The answer is a line. There's a kind of a line of lines which are contained in the stack through L. So to describe all the lines in 2 space, we could start off by thinking about this circle representing the pencil of lines through P, and then to every point on this circle we associate a line. The line representing the stack of lines which are parallel to the line through that point. So topologically, sort of geometrically, we need to glue a line to every point on the circle. So if we think of this circle and gluing a line to each point on the circle, then we'll have a parameter space for the set of all lines in the plane. What makes this interesting is that there's more than one way of gluing a line to every point on a circle. In fact, there are two ways of doing that. So here are the two ways of gluing a line to every point on a circle. The simple, sort of naive way is to take your circle, say as the equator there, and simply glue a line on every point, giving us a cylinder. Now this line here is actually infinite line, so it actually extends in all directions, so this is actually an infinite cylinder. So that's one possibility for the space of all lines in the plane. Another possibility, a little bit more subtle one, is to glue the lines around with a twist. We get something called a Mobius band. And here's a picture of it. This is the central circle, the red one here. And what we're doing is there's a line, or part of a line. I can't represent the whole thing very easily. So just imagine that line there. It's glued to the circle and we move around like this. But as we get closer to this point here, these lines come together and twist before they connect again. So if you think of this as being the vertical line, in the first case of a cylinder we had a situation like this. We had a circle of lines. In the second case we have a situation where we have a circle of lines around like this, but as we are coming around we are rotating at like this. Okay? Come around, we're rotating. To give a model with a piece of paper, here is a little strip. The cylinder is obtained just by gluing things together in the usual way. That's a cylinder, sort of a base circle and lines fibering. With the Mobius band we take the cylinder also, but before we glue it together we make a little twist like this. Okay? So now it looks a little bit different. It's a twisted object, but you should still think of it as having a central circle and lots of lines associated to each point on that central circle, but there's a twist in it. So a natural question is, which of these two actually represents the lines in the plane? It turns out that it's the Mobius band that does. And to see that is a kind of a cute argument. There's something topologically different about this one and this one. Well, there are several things that are different, but one way of saying what a difference is that if you take any loop on the cylinder, just draw a little closed circle. If you cut along that loop, then the cylinder breaks up into two pieces. In this case, if you cut along here, you would get the inside versus the remainder of the cylinder. You'd have two different pieces. But even if you took this loop here, which goes around, and you cut along there, then the cylinder would break into two disjoint pieces. That's a property that the Mobius band does not have. It's true enough that if you took some small loop like this and you cut it out, then there would be two pieces. But if you chose this equator to cut, then you could cut along the Mobius band just like the model I made. You can do this at home, make a Mobius band, cut along the thing. You will find that when you finish the cut, the thing falls apart, but it doesn't fall apart into two pieces, because the things that were on top of the circle over here are connected to the things on the bottom because of this overlapping twist. So that's a difference between the Mobius band and the cylinder. If you remove a circle from the cylinder, you always get two different pieces. In other words, you cannot connect a piece inside to a piece outside. So how can we see that the lines in the plane are really a Mobius band and not a cylinder? We can use this property. So the analog of cutting out a circle is to consider a pencil. a pencil of lines through a point P, that naturally forms a circle in the space of all lines. So suppose we cut out that particular circle. So in other words, we exclude the pencil of lines through the point P. We remove them from consideration and ask, the stuff that remains, is it connected or not? Can we go from any one line to any other line in a continuous way? So for example, here's an arbitrary line L, which is not in the pencil. Here's another line M, which is not in the pencil. Can we go continuously from this line to this line, avoiding the pencil? Well, if you think about it naively, you might say, well, no, you can't, because if you try to go from here to here, somewhere in there we would pass through P and then we'd be connected through to the pencil. But that's not the only way you could get from L to M. You could also get from L to M by going this way, taking this line and moving it around like this to M. In this way, I can move from any line in the plane to any other line in the plane by avoiding the pencil P. In other words, by never going through P. So what I've kind of convinced you of here, I hope, is that if you remove the pencil at P, you can still connect any 2 points in what's left over. So that means we're not in the cylinder case, we must be in the Mobius band case. The space of all lines in the plane is a Mobius band, and it's, in my view, the most natural and most pleasant manifestation of the Mobius band in mathematics. It should be in every linear algebra text. Alright, so now let's go to a level up to 3 dimensions, and let's talk about lines and planes in 3D. When we move to 3 dimensions, the first thing to realize is that the analog of a line is a plane. Although we have points, lines, and planes in 3 dimensions, the planes are the ones that act most like the lines in 2 dimensions. Lines in 3 dimensions are in fact more complicated, as we'll see. So let's talk first about planes in 3D. A plane is given by a single equation in x, y, and z. And it can be described in terms of 3 points that lie on the plane. So here we have a plane through the points 3, 0, 0, 0, 1, 0, 0, 0, 2. These are points on the coordinate axes. There's 3, 0, 0, there's 0, 1, 0, and there's 0, 0, 2. And I've drawn the plane by joining the points by lines. So those lines lie in the plane, and you should think of this plane as being sort of at an angle to the coordinate axes, cutting them at those 3 points. This is the equation of this plane because each of these points satisfies the equation of the plane. This is called the Cartesian equation of the plane, and it's a direct analog of the equation for a line in 2 dimensions. We're just adding one more variable. So some special cases involving this plane. If we set x equal to 0, that term becomes 0, then we get an equation only involving 2 variables. 6y plus 3z equals 6, or if we divide by 3, 2y plus z equals 2. What's the meaning of that? Well, when we set x equal to 0, we're talking about all those points in 3 dimensions whose x-coordinate is 0. In other words, that lie in the plane spanned by the y and the z axes. That's a coordinate plane. That's in the picture. If you think of x as coming out at you and y and z as being in the plane of the wall, then we're just talking about the wall. So when we set x equal to 0, we're restricting what happens to the plane just viewed from this coordinate plane. And what we get is that line joining these 2 points in that plane, and that line in the y and z coordinates has this as its equation. Similarly, if we set y equal to 0, then we're talking about the coordinate plane through the x and the z axes. So that's that plane there. And that intersects our given plane pi in this green line here. So that's a line in the xz plane, and its equation in that plane is determined by setting y equal to 0 here. 2x plus 3z equals 6. That's the equation of that line in the plane of x and z. And if we set z equal to 0, then we're talking about the horizontal plane, the xy plane. Set z equal to 0, then you get 2x plus 6y equals 6, or dividing by 2, x plus 3y equals 3. And that's the equation of that ordinary line there in the xy plane. Two planes generally meet in a line. If we have three planes, well, two of them meet in a line, and then the third plane meets that line in a point. So three planes generally meet in a single point. However, there are exceptions. If the three planes have two parallel planes in them, then there's no common meet. Here's an example of three planes. There's one equation, there's another equation, there's another equation. Those are each representing planes in our three-dimensional space. So suppose we want to find the common point of those three planes. It means we have to solve this system of equations. We know how to do that. We rewrite this in matrix form. There is the coefficient matrix for this left-hand side. Here are x, y, and z, the variables. And here is the vector of numbers on the right-hand side. And to solve this, we have to multiply by the inverse of this matrix on both sides. The determinant of this matrix is 1 times this 2 by 2 determinant, 7 plus 4, that's 11, minus 3 times this 2 by 2 determinant, that's 2 minus 2, that's 0, plus 4 times this 2 by 2 determinant, 4 minus 7, that's 11, for a total of 55. That's non-zero, so this matrix is invertible. How do we find its inverse? Well, let's do it in a few steps. The first step, and the one that involves the most work, is to find a lot of little 2 by 2 determinants. So to do that efficiently, let me introduce a new notation. Let's say that the d-min of this matrix is the matrix of determinants of minors. It means that for every position, over here, I calculate the determinant of the corresponding minor. So in this position, it would be 7 minus 4, that's 11. So we'll call that the d-min of this matrix. It's just a notation to allow us to say explicitly going from here to here. We've already calculated these three determinants and their minors. The determinant of the minor corresponding to this one would be 3 minus 8, that's minus 5. And this one will be 1 minus 4, that's 5. This one here, determinant 2 minus 3, that's 5. Over here, minus 6 minus 28, and that's minus 34. Right here, minus 2 minus 8, that's minus 10. And last but not least, here, 7 minus 6 is 1. That's the majority of work to calculate the inverse. Let's call that the d-min of the original matrix, the matrix of determinants of minors. So to calculate the inverse, what do? We take 1 over the determinant, there's 1 over 55, and we take this matrix and we transpose it first of all. So instead of going across here, we go down. Instead of going across here, we go down. Instead of going across here, we go down. And after we've taken the transpose, we multiply all of these odd positions by minus 1. So I've done that. There was a minus sign there. I've changed it to a plus. There was nothing there. I put a minus sign there. There was a minus sign here. I've changed it to a plus. So this right here is the inverse matrix to this one. And I've multiplied both sides by that inverse matrix. So there's just x, y, z on the left-hand side. And now we have the inverse times our vector minus 3, 1, minus 2. And what do we get? Minus 3 times 11, that's minus 33, plus 0, minus 22, that's minus 55. Divided by 55 is minus 1. And over here, minus 15 plus 5 plus 10, that's 0. And over here, 3 times 34, that's 102. Plus 10, that's 112. Minus 2 is 110. When we divide it by 55, we get 2. There's a solution. X, y, and z. So the common point of intersection is the point -1, 0, 2. I've written it as a row vector in square brackets because it's a point. And we can check that. We can check that that point satisfies these equations by plugging things in. For example, -1 plus 0 minus 2 is indeed -3. And -3 plus 0 plus 4 is indeed 1. And -4 plus 0 plus 2 is indeed -2. So this really is common point of those three planes. Now let's talk a little bit about lines in 3 dimensions. A line can be described in a number of different ways. Perhaps the simplest way is to just think of it as determined by 2 points. If you have 2 points, then there's a unique line through those 2 points. Another way is to think about it in terms of a point and a vector. If we have a point and we have a direction vector, then there's exactly one line through the point with that direction vector. Another way to think about a line is as the intersection between 2 planes. Given 2 planes, the meet is a line. So that's another way of describing a line, is by giving 2 planes which intersect along the line. Let's start with the 2 points idea. So let's start, say, with this point A, which is 3, 1, 1. So there is part of the box to create it. And the point B, which is 2, 2, minus 1. 2 in this direction, 2 in this direction, minus 1 in the z direction. So it's down here. And those 2 points determine a line. Let's call that line L. Now, in terms of affine combinations that we talked about earlier, we can think about a point on this line AB, there's our notation for the line, as a combination of the points A and B determined by a parameter lambda. 1 minus lambda A plus lambda B. And we can rewrite that by bringing the A out and thinking of it as the point A plus lambda times the vector AB, because the vector AB is the difference between the coordinates of B and A. So for example over here, we can think of this line as being described by, first of all, the point A, which is 3, 1, 1, plus lambda times the vector joining A to B. What is that vector? We get it by taking the difference between the coordinates. 2 minus 3, that's minus 1. 2 minus 1, that's 1. And minus 1 minus 1 is minus 2. So the vector AB from here to here is that vector there. And I've written it in the column to remind you that it's actually a vector. So there's a point plus lambda times that vector. In other words, you can start at this point and you can go any multiple of this vector, either in this direction or in this direction if the multiple is negative. So that's a parametric equation for this line. It has 2 ingredients, the point on the line and the direction vector of the line. And these 2 things are not unique. Point on a line, we could have chosen any point. And the direction vector, well, we could have chosen any multiple of that, multiplied by 5 or minus 3/2, and it would still be a direction vector. A line has not only a parametric equation, it also has a Cartesian equation. Cartesian equation means that it's an equation involving x, y, and z, our basic coordinates in our Cartesian framework. So let's have a look at that same line we've just been talking about. 3, 1, 1 plus lambda times this vector minus 1, 1, minus 2. And now let's think about that point on that line as being x, y, and z. And we want to find a relation or relations between x, y, and z that determine the line. So the first thing to do is to realize that there are really 3 equations here. There's one equation for the x coordinate, which is 3 minus lambda equals x. Then for the y coordinate, 1 plus lambda equals y. And 1 minus 2 lambda equals z. So this single equation involving vectors and points is equivalent to these three equations just involving the numbers. And we can solve for lambda. We can bring the 3 on the other side and divide by -1. So we get lambda equals x minus 3 over minus 1. Here, lambda equals y minus 1 divided by 1. Okay, we don't really need that, but I'll put it there anyway. And here, bring the 1 to the other side, z minus 1 divided by the coefficient minus 2. So we've solved for lambda, and now we can forget about lambda, because we know this has to equal this, has to equal this. This relation between x, y, and z, and there's really two equations here. There's really this equals this, and this equals this. So I've written it as one equation, but there are really two separate equations there. This is the Cartesian equation of the line, or a Cartesian equation of the line, because it's highly non-unique. How is it related to the original parametric equation? Well, you can see the relation, I hope, that the point 3, 1, 1 ended up here, 3, 1, 1. They're the numbers that we subtracted from x, y, and z. And the direction vector minus 1, 1, minus 2 ended up here in the denominators. Minus 1, 1, minus 2. So the point on L occurs in the numerator, and the direction vector for the line is in the denominator. So you can actually, once you've done this a few times, you can go immediately from here to there without going through that intermediate calculation. And I point out once again that this is highly non-unique because we could replace the point 3, 1, 1 with any other point on the line. And instead of the direction vector, we could multiply that by any scalar and it would still be the same. And I've already pointed out that it really is two linear equations. And what is a linear equation? A linear equation, we've said, is a plane. So this description of a line in Cartesian form is really telling us two planes that meet in a line. So there's our line. And we found one plane. That's that plane there, the plane x minus 3 over minus 1 equals y minus 1 over 1. That's a plane. And there's another plane, this equals this, determines another plane. And those two planes meet in our line. And again, those planes are highly non-unique. You could change them as long as they all go through that line. There's an infinite number of possibilities. So there's the parametric equation for a line. There's a Cartesian equation for a line. Let's do another example like that has just a little twist in it to be careful about. So here's another parametric equation for a line. The line through the point 4, minus 1, 5 with direction vector 2, 0, minus 3. And I've written down the three equations. 4 plus 2 lambda equals the x-coordinate. Minus 1 plus 0 equals the y-coordinate. And 5 plus minus 3 lambda equals the z-coordinate. Now if we do what we did last time, we solve for lambda for each of the equations. But notice what happens. The first equation, we get x minus 4 over 2. Fine. But then the second equation, there isn't a lambda in there. So we can't really solve that second equation for lambda. Alright, so let's carry on with the third equation. We can solve that for lambda. We get lambda equals z minus 5 over minus 3. So we can get this equals this. Well, what about that second equation? Well, that's just a separate equation. We just repeat it over here. Now, if we ignore the lambda, then we see we still have two equations, but they're a little bit different in relation to each other than previously. We have this as one equation, that's one plane, and y equals minus 1, that's another plane. That's a plane parallel to the xz coordinate axis. Okay. So that's still a plane, that's a plane. Those two planes together, those two equations, determine the line. So this is a Cartesian equation for that line. Alright, so here's a little example of a problem. Suppose we are asked to find the meet of the line L with this parametric equation and the plane pi with Cartesian equation x plus 3y minus z equals 5. So we have a given line, we have a given plane, we want to find the point where they meet. Well, it's not too hard. We're going to substitute x, y, z. This is the equation of the line written out in coordinates. Just combining the x, the y, and the z. The x is altogether 1 minus lambda. The y is 2 plus 4 lambda. The z is minus 3 plus lambda. That's another way of writing this. So I'm going to plug this into our equation of the plane. There's x, there's y, there's z. So we get, there's x, 1 minus lambda, plus 3 times y, minus z. And that should equal 5. All right, that's a single equation involving lambdas. And how many lambdas are there altogether? There's minus 1 there, plus 12, minus 1, for a total of 10 lambdas on the left-hand side. And then if we bring all the constants to the other side, there's 5 to begin with. What else do we have here? We have 1 plus 6 plus 3. That's 10. If we bring that 10 to the other side, we have to subtract it. So we get 5 minus 10, that's minus 5. And so lambda is minus 1/2. And then to find the actual point, we plug minus 1/2 into here to get 3/2. Minus 1/2 here, that'll be 0. And minus 1/2 here, we get minus 7/2. And so that is a point which lies both on this line and on this plane. You can check that if you put 3/2 in here, 0 there, minus 7/2, then we're going to get 3/2 plus 7/2. That is indeed 5. That's 10/2. So we found the place where the line and the plane meet. All right, now let's have a go at a slightly more challenging problem. Suppose that we have two planes and we want to describe the line of intersection, the line in which they meet. Okay, so we're going to talk about the meet of two planes. And let's look at an example. Here's one plane given by a single linear equation. And here's another plane given by another equation. And here's the picture that we have in our mind. There's one plane somewhere like this, another plane somewhere like this, and these two planes are meeting in a line. We want to describe that line. Okay, so, well, the thing is, a line is determined by a number of points, say 2 points on the line. So one way of finding this line is to find 2 points on the line. And one way of finding a point on the line is to intersect these 2 planes with a third plane. If we take a third plane, an arbitrary third plane, it's going to meet that common line in a point. And the advantage of using a third plane is that we know how to find the meet of 3 planes. That's what we've already done before. But we want to do this not just once, but we want to do it twice so that we can determine the line of meeting. We don't want just 1 point on the line, we need 2 points on that line to determine it. So we're going to do a little bit of a trick here. We're going to kill 2 birds with 1 stone by introducing a third plane which has a variable in it. And that variable is going to allow us to find 2 different values at once. And the third plane that we're going to introduce is going to be of the simplest possible kind because we don't want to make life harder for ourselves. We're going to introduce the plane with equation z equals lambda. Lambda is a parameter, like 1 or 2 or 0. So that's a plane that's, in this case, parallel to the xy plane. It's a horizontal plane. And we're going to throw that into our 2 equations that we already have. Now we have 3 equations. So we can write down the system for it. There's the coefficients of the first plane, there's the coefficients of the second plane, and our third plane just has a single z in it. On the right hand side, minus 3, 1, and lambda. This lambda doesn't bother us. We don't need numbers on here. We know how to invert this even if these are variables. So that doesn't bother us. We're going to do exactly what we did before. We calculate the inverse of this matrix. We multiply both sides by the inverse of the matrix. Then we find x, y, z in terms of these numbers, including the lambda. How do we find the inverse of the matrix? That's the main problem. Here is the d-min of that matrix. It's the matrix formed by determinants of minors of this original matrix. So I'll let you check that these are the determinants of the minors of that matrix. And the determinant of this matrix here, that's relatively simple to find if we expand along this bottom row. Plus, minus, plus, minus, plus. So it's plus this, plus 1 times this 2 by 2 determinant, which is 7 minus 6, or 1. So the determinant here is 1. It's a very simple calculation because there's this row essentially of mostly zeros. So the inverse matrix is then obtained by taking this d-min matrix. First of all, doing 1 over the determinant, but 1 over 1 is 1, so we don't bother. Then this transposed. So there's the transpose of that matrix, followed by putting minus signs in these odd places. And then when we multiply by minus 3, 1 lambda, we get an expression involving not just numbers, but also some lambdas. And what is this telling us? This is telling us the point of intersection of these three planes, where the third plane has this variable parameter in it. So as that lambda varies, we're getting all the intersections between these three planes. In other words, we're running along the line of intersection of the original two planes. And what is that point? It's up here, right here. I've peeled off the constant term, the stuff not involving lambdas, minus 23, 10, 0. And then I've taken the stuff involving lambdas and written it as plus lambda times 11 minus 5, 1. That's the parametric equation of a line. It's a line through this point with this as the direction vector. And that is the line of intersection, or the meet of these two planes. And we can check that in the following way. First of all, we can check that this point really does satisfy both of these two equations. Minus 23 plus 20 minus 0 is minus 3, yes. Minus 23 times 3, that's minus 69. Plus 70, that's 1. Plus 0, that is indeed 1. So this point really does lie on both of those planes. Now what about this vector? What should its relationship be with these two planes? Well, this is the vector of the direction of the line. It's the common direction that both planes have. So this should be a direction vector which is in the direction of both planes. If we plug this in to the left-hand side, what happens is we get 11 minus 10 minus 1, that's 0. That's telling us that if we add a multiple of this vector to a solution, the solution's not changing. In other words, we're still staying on the plane. That's the meaning of that. And if we plug this vector into the left-hand side here, we get 33 minus 35 plus 2, that's also 0. Telling us that if we change x, y, and z by adding this amount, then we're still staying on the plane. So that really is a direction vector for both planes. So we verified or checked our solution in terms of our original data. This is a very interesting idea. It's a method that's found in almost no linear algebra texts, because most linear algebra texts do not emphasize the formula for the inverse of a 3 by 3 matrix like we have been doing. We've so far completely avoided row reduction, almost completely, in our development of the theory. This is a big advantage, a big conceptual advantage for you. And this is our way of introducing parameters into situations where we have fewer equations than variables. So we'll keep that in mind for later. A natural question that you may have on that previous example is, why did we introduce the third plane in the form z equals lambda? Why not x equals lambda or y equals lambda? In fact, we could have done either of those two and we would have still gotten a correct answer. So sometimes, usually, it doesn't matter which we choose, but sometimes it does matter. Let's have a look at an example like that. So here is another example of two planes. Plane x plus 3y minus 2z equals 2, and the plane 2x plus 6y minus 5z equals 3. Suppose we want to find where those two planes meet. Well, if we introduce the third plane z equals lambda, just like we did in the previous example, then the matrix that we would get would be 1, 3, minus 2, 2, 6, minus 5, 0, 0, 1. And if we calculate the determinant of that matrix to see if it's invertible, we would calculate from here, it would be this times this 2 by 2 determinant, and that 2 by 2 determinant is 0. So the determinant of this 3 by 3 matrix is 0. It means it's not invertible. You cannot invert that matrix. So you cannot solve the system and our method fails. What we've done wrong is we've introduced the wrong plane, because this little 2 by 2 matrix was 0. So in this case we should use y equals lambda or x equals lambda. Let's use y equals lambda. So then our third plane is y equals lambda, and the system looks like this. Okay, you can check then, going through the same story. There's the d min of that matrix. The determinant is 1. The inverse of our original matrix is right there. I've multiplied both sides by the inverse, obtained from this d min by taking a transpose and multiplying by minus 1s. Then we multiply through, we get 4 minus 3 lambda, lambda 1. We separate that out, 4, 0, 1 plus lambda minus 3, 1, 0. We do get a line, the line of intersection or the meet of those two planes. It's also useful to have a parametric equation for a plane. So if we have a plane pi, and if we know 3 points on the plane, and those 3 points are not all on a line, so they're not collinear, we can say that the plane is determined by those 3 points. We'll just write pi equals a, b, c. Then we can introduce direction vectors for the plane in terms of those 3 points. We can look at the vector, say, joining a to b, call it v, and the vector joining a to c, call it u. Those are direction vectors for the plane. They are vectors which lie in the plane. So for example, if the plane is the plane of the wall, then this is a direction vector. So this is a direction vector for the wall. So is this a direction vector for the wall. So is this. Even though the vector is not actually in the wall, I can translate it so that it lies in the wall. That's a direction vector. However, this, pointing towards you, is not a direction vector for this plane, because even if we translate it, it doesn't lie entirely in the plane. Of course, a plane has many possible different direction vectors, and we're just choosing 2 of them. So they are highly non-unique. But then we can describe the plane, or a general point on the plane, in terms of the original point A and these 2 directions. We can say that we can get to any point on the plane by starting at A and going some multiple of V plus some multiple of U. We can write it this way. An arbitrary point P on the plane can be written as start with the point A, move in the direction V by a multiple lambda, say, and then move in the direction U by a multiple eta. So for example, suppose that A was the point 1, 0, minus 1, B is the point 2, 1, 3, and C is the point minus 4, 2, 5. Then the plane determined by them, we can express it parametrically by saying we could start at the point A and go a multiple of the vector AB. How do we write down the vector from A to B? We take the difference between coordinates. 2 minus 1, 1 minus 0, 3 minus minus 1. So that's the vector joining A to B. And here is the vector joining A to C. Minus 4 minus 1, 2 minus 0, and 5 minus 1, 6. So every point in this plane can be expressed as a combination of this point plus some multiple of that vector plus some multiple of that vector. It's a parametric equation for the plane. Now a natural question is, how do we go from the Cartesian equation involving x, y's, and z's to the parametric equation and vice versa? So first let me show you how to go from the parametric equation of a plane to the Cartesian equation of the plane. The parametric equation of a plane looks like this. It has a reference point on the plane and then two direction vectors for the plane. We start at the point and we go any multiple lambda of the first vector v plus any multiple, say, eta of the vector u. And that should be an arbitrary point x, y, z on the plane. Now we want to go to an equation which is Cartesian. In other words, simply a linear equation in x, y, z representing the same plane. Okay, so here's the picture. There's our point A. There's our vector v, which lies in the plane somewhere. There's a vector u, which is another vector lying in the plane. Here's an arbitrary point P in the plane. And what's the relation that we can use? The relation is that the vector joining A to P is in the same plane as the vectors v and u. All three of these vectors lie in a plane. Now, how do we capture that algebraically? Well, we remember the determinant. The determinant we originally thought of in terms of a trivector. We have three vectors. The determinant represents the volume or the signed volume of the parallelepiped formed by those three vectors. And if those three vectors are coplanar, then that determinant is 0. So that determinant being 0 is telling us that the vectors are coplanar. And that's the criterion that we're going to use. Because the determinant is just this determinant of a matrix. So we can write down the vector AP in one column, the vector V in another column, the vector U in another column. And we can calculate the determinant of that. So how do we calculate AP? The vector joining this point to this point. It's just the vector whose coordinates are x minus 1, y minus 0, and z minus 1. So there's the vector AP. And I've copied the vector v, and I've copied the vector u, and now I'm going to take the determinant of this thing and set it equal to 0. That's the condition of coplanarity. That will be the condition that tells us that P lies in this plane. So what's the determinant? X minus 1 times this 2 by 2 determinant. 6 minus 8, that's minus 2. Minus y minus 0 times this 2 by 2 determinant. 6 plus 20, that's 26. And then plus z plus 1 times this 2 by 2 determinant. 2 plus 5 is 7. So if we set that equal to 0, then collect all the x, y's, and z's on one side and all the constants on the other side, what do we get? We get minus 2x minus 26y plus 7z on the left-hand side. And on the right-hand side, over here there's a 2, there's 0 here, and 7, so there's altogether a 9 here. When we bring it to the other side, we'll have minus 9. So there is a Cartesian equation for that same plane as this is describing. So that's how to go from the parametric equation to a Cartesian equation through a determinant. In standard linear algebra courses, the inner product and cross product are used here. But we have not introduced the inner product and the cross product. Those are in fact metrical objects that depend on notion of perpendicularities and notion of distance. This is a purely affine derivation of essentially the same thing. It's in some sense more fundamental than the treatment that you find in most linear algebra textbooks. Something to think about. Going from a Cartesian equation of a plane to a parametric equation is pretty simple. all we need is 3 points on the plane. So if there's our plane, 2x minus 3y plus z equals 5, we just have to cook up 3 points which lie on the plane, and it's easy to do that because we just let any two of these variables be anything we want and we solve for the third one. And we use simple values, so let's say let x be 1 and y be 0, then z has to be 3. If we let x and y be 0, then z is 5. If we let this be 2 and this be 1, for example, and that would be 4 minus 3, that's 1, then z has to be 4. Okay, so there's 3 out of billions of points you could have chosen. And once you have the 3 points, you just write down the parametric equation of the plane in terms of one of the points, say point A, plus the 2 vectors formed by, say, AB and AC. You can also use BC. It doesn't matter which vectors you use as long as you have 2 vectors in different directions lying in the plane. The vector AB, this minus this, is minus 1, 0, 2. And the vector AC is this minus this, that's 1, 1, 1. So there's an example of a parametric equation, which is of course much less canonical than this one. This one's unique up to scaling by constant. You can multiply this equation by 5 and still have the same plane. But other than that, this is a unique form. So the Cartesian form is really, in some sense, preferable to the parametric form, but the parametric form is quite useful in many concrete situations. Now let's have a look at some exercises. We've done a lot of stuff this lecture. Time for you to practice. All right, only 2 exercises today, but the first one's a little bit long. So our first exercise here are 3 planes. Let's call them pi 1, pi 2, and pi 3. And I want you to practice visualizing things. So first of all, sketch each plane in the usual x, y, z coordinate system. Secondly, find parametric equations for the lines obtained by meeting any 2 planes. So any 2 of these planes meet in a line, we expect, and I want you to find parametric equations for those lines. Let's call, say, the meet of pi 1, pi 2, pi 1 wedge, pi 2 with a down wedge. And here are the 3 meets, and also find Cartesian equations for these lines as well. So you want to understand the 3 lines formed by these 3 planes. Parametric and Cartesian equations for those lines, please. And find the common meet between the 3 planes. So that'll be the place where these 3 lines also meet. And the second exercise, find the Cartesian equation for this plane, given here parametrically, and where does that plane meet this line given in terms of Cartesian equation. Okay, so we've done well lines and planes, equations of them, very important basic understanding for 3-dimensional geometry. Now we're in a position to think about transformations of 3-dimensional geometry. Reflections, dilations, rotations, projections, all kinds of very practical applications of 3x3 matrices, essentially. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.